Hi students, in this video we're going to look at how to calculate the physical area between a function and the x-axis. So after watching this video you should be able to understand the difference between algebraic and physical areas. You should recognize that integration gives us an algebraic area and then use that fact along with a couple of other skills to determine the physical area between some function and the x-axis. Big things to remember: our fundamental theorem of calculus. So the area under the curve f of x between a and b is given by our formula up here. And then remembering our integration rules too. Okay, we'll use those pretty regularly over the course of this video as well. Alright, so our first thought is to try and calculate the area under the graph, sine x, between 0 and 1,000. Now, before jumping straight into this one, I do want to have a little thought experiment, I guess you could call it, thinking through what this will look like. So our sine curve, there's 0. Our sine curve will go up and down, starting from 0 all the way along. And eventually we're going to end up at 1,000. Now, if you were thinking about this problem and it's working out what the area is, would you expect the number to be a very large number or a very small number? Because from the diagram, it looks as though it should be quite large. It's because we've got a bunch of these areas here, 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 and if we add them all together, we should, especially over a distance of 1,000 units, we should get a number that should be pretty large. So let's evaluate. If we want to find the integral from 0 to 1,000, sine x dx, I'm not going to do work for this one, we're just going to pretend we're using a graphics calculator here, typing it in, getting our solution. And we find out the area under the sine x curve between 0 and 1,000 ends up being 0.1731, etc. Not a big number, a very small number in fact. But over a distance from 0 to 1,000, the big question is, well, why is that the case? Why is this area so small underneath between the sine x function and the x-axis over a distance of 1,000? Why is it so small? See, when we're calculating, or when we're using integrals, okay, where the graph is at any particular point is very important. Because when we do some integration, what we call it gives us what we call the signed area, or the algebraic area. You see, every region above the x-axis it will treat as positive, and every region below the x-axis it will treat as negative. And so what's going to happen is, for each cycle, these areas are going to cancel out because they are exactly the same. So that'll be 0. Then the next two, that'll be 0. And so on. And what's going to happen is, once we get to around about 1,000, let's just say 1,000 might be here, all that's left to calculate is this tiny little area here on the end, because all of those positive and negative areas cancel each other out. So integration determines the algebraic area, or the signed area. It doesn't actually give us what we would call the physical area. So the physical area would involve us adding each of these components together to determine overall what is the actual area, when integration says, actually any areas below the x-axis, those areas we're going to call negative. So if we do want to find the physical area, we need to have some other sort of approach. Basically what we need to do is to look at our regions, our positive and our negative ones, just change them all to positive regardless of whether they're positive or negative numbers, just change them all to positive and add them all together. So to determine the physical area between f of x and the x-axis on some interval a to b, the big important factor we need to take into account are the x-intercepts, and if there are any x-intercepts on our interval. Because if there are some x-intercepts there, that indicates we may have some positive areas above the x-axis and some negative areas below, which we don't want to cancel out if we're working out the physical actual area. So we need to know what those intercepts are. If any of the intercepts are on the interval, then that means we need to change our approach slightly when doing our integration. If there's no intercepts on the interval, that's fine. Just calculate your interval. If it's a negative number, change it to positive. If it's positive, hunky-dory. But if there are x-intercepts on that interval, we basically need to break our area or our integral function into two smaller integrals with that x-intercept point being our bound. And once we've done that, we can change the areas to positive, we can add them together and get our physical area. Alright, so now let's look at an example. So we have to calculate the physical area underneath our curve between x equals 1 and 4. Looking at our sketch here, you might say that x1 is going to be about here. x4 could be on the inside of our parabola. It could also be on the outside. So we could have like a positive area there and a negative area there. And doing a straight integral may not give us the physical area because some of that negative area will cancel out some of the positive area. We may need to work out those two areas separately. So our first step to finding physical area is determining whether or not there are any x-intercepts. So we're going to find x-intercepts by letting y equal 0. So 0 equals 5x minus 2x squared plus 3. I'm going to rearrange that one because I don't like the leading coefficient of my quadratic being negative. So let's rearrange it to the other side. It'll be 2x minus 5x minus 3 equals 0. Now at this point, I've got a quadratic here to solve. What we can do is try and factorize it. So we've got 2 and negative 3. I need numbers at times to give negative 6, but add to give negative 5. It's pretty clear those numbers are going to be negative 6 and positive 1. So I can write that out for us. 2x squared. We said there were going to be negative 6 and positive 1. So negative 6x plus x minus 3 equals 0. Factorizing out, that'll be 2x outside of x minus 3. Now we've just got x minus 3 there, so I'm just going to put a 1 out the front. X minus 3 to help with the factorizing. And so I'm left with here x minus 3, 2x plus 1 equals 0. So then we are looking at using null factor law, therefore x equals 3 or x equals negative half. And so those are our x-intercepts. Now here we were right, that x-intercept of 3 is indeed on our domain. So that means we will need to work out our integrals separately, make sure they're both positive, and then add them together in order to determine our physical area. So we've got our physical area here. We're going from 1 to 3 of 5x minus 2x squared plus 3 dx. And that's going to equal, the answer is 26 on 3. And then if I do the integral from 3 to 4 of 5x minus 2x squared plus 3 dx, put that into a calculator, I end up getting 25 on 6. Also, that'll be negative 25 on 6. And so if I want to find the physical area, I just need to make sure I change all the numbers to positive and add them up. So the area going to be 26 on 3 plus 25 on 6. It's going to be 52 on 6. 52 and 25 is 77 on 6 square units for that physical area. So after watching this video, you should be able to understand the difference between algebraic and physical areas. You should be able to recognize that integration helps us work out the signed or algebraic area, and then determine the physical area between f of x and the x-axis by using intercepts to help us find positive and negative regions.